We think if we have this limit, I mean this one, this is just a rewriting for a simpler, it's by identity. If you have base and exponent, you can write it as e to this exponent, to like the exponent times the base inside the logarithm, inside an exponent. And we see the limit value, oh actually this is 2 pi over 4, still is the same. And we want to solve this, which is the same as this of course, as x goes to pi over 4. But a way we can do it is also just focus in this one. It will be practical to focus on the exponent only. So we will first just take care of what's circled here, and then we will take e to whatever that result is eventually, but it will take some while. So we have still the same limit value, but of just the argument, the exponent there. Because we can, in fact, like this, we can actually do this and then get the result. It will be a constant in the end. And then we will say basically this limit is equal to e to whatever this ended up being. And that works because e to x is defined for all real numbers input, so it's fine. But anyway, let's now talk about how this is gonna go. So actually we'll use some theory of trigonometric substitutions a bit. We'll also use substitution for a known limit. And concretely the known limit we'll be using is the following. That is, we will use this fact that ln of x plus 1 over x equals, if x goes to, or the independent variable, whatever it happens to be, it could be y plus 1 and y here, and y to 0, is 1. So we have this identity. For that, what we can start with is I can rewrite, basically, this is ln of tangent x. So we want to somehow get rid of the ln. So the way we'll do it, we'll use this sort of substitution or this identity, and on that we'll base a substitution. So in our actual expression we'll get a y, but actually it will be good because the pi over 4 really helps here. The pi over 4 will take the substitution variable to 0. That will be very useful. So what we will get is basically the following. If I want ln and the independent variable to be in the form, the independent variable plus 1, and I cannot call it x again because I'm doing the substitution, so let's call it different. Let's try to get y plus 1 over y. Then tangent x, I'll say is y plus 1, and then we'll somehow divide this whole thing by y plus 1 and also multiply it on the top by y, and multiply it on the top by y to make it multiply and divide by the same new thing, not to change the expression, but we'll put the expression, we'll put the substitution idea here already. The idea is, if I want y plus 1 here in order to kind of start matching this thing, in order to eventually get rid of the ln, I'll say that tangent x is equal as close as possible, so y plus 1. Then I'll also try to devise how to generally rewrite y, so that will always be tangent x minus 1 now. So I can rewrite it. Well, first of all, I can actually think of this as sort of break it up into two parts. Or actually, yes, officially I should mention the new limit bounds, or I can still talk in terms of x and then kind of realize the changes that will be there. So let's, for now, just rewrite it similar as it was. That is, this will still equal limit x to pi over 4. This thing stays for now, 2x, and we multiply by ln of y plus 1 because we want that, and let's multiply and divide by y, so we get this sort of form already. So we will get y here, and we should also multiply on the top by y because that y was unanticipated and it would change the expression otherwise. Alright, well, now it works out, but in a second we also have to change the y to this expression because we will calculate the rest in terms of x. Thanks to this expression, we can cancel out this part. This will go to 1 because this tells us that such a thing goes to 1. By the way, we should not just cancel out that fast. To be a little bit more concrete, let's rewrite this. Let's keep exactly the same expression. I'm just gonna get rid of the crossing, so it's gonna basically, I'm just gonna switch it. I'm gonna do the same thing, but we should realize that For this part, a limit as y approaches something will apply. We want y equals to 0, y goes to 0 for this to be 1. But it will actually work out. Because our substitution, what it did is it said y is tangent x minus 1. But inside the original limit is going to pi over 4. That means for x going to pi over 4, we have to plug it into this expression, tangent x minus 1. Tangent pi over 4 minus 1 is actually 0. So that's very nicely working out. So what we actually have here is sort of this. For the x things, we have still x goes to pi over 4. And then we have basically this. Well, let's just not make it confusing. It would make more sense to rewrite things. Now we have y goes to 0 because that's what happens for x going to pi over 4. And then the things that are in terms of y will rewrite in like another limit that's multiplying the original. So we see we have like two limits. But this thing goes to 1 according to something going to 0 ln something plus 1 over something. And then we have just y going to 0 left. But actually, instead of saying y going to 0, we should realize what y is according to the substitution, that is tangent x minus 1. So that has to stay there. So we'll take the y back out, we can put it here, but we will rewrite it in terms of x now that we will have it inside the limit of x again. So this main part of the y limit cancels to 1 according to this identity. Now we can rewrite this, we can take out the y, that doesn't matter, as long as we're not cancelling it out according to such an identity that requires the limit go to 0, right? So we have this times y, but that's what's left. Actually, this wasn't cancelled out. We just also multiplied in the numerator, once again repeating this fact in order to maintain this equilibrium between the denominator and numerator, because y was divided in order to match this identity. But the y still stays, the numerator one. But y is tangent x minus 1. So we have this, we now have this thing. So this is our remaining limit we now have. And once we tackle this, the result of this, we will basically get the exponent's value. So we got rid of the ln x, and this is still equivalent to where we started. But we see now, instead of ln 10x, we have 10x minus 1. So let's delete some things. This substitution we will no longer use, so I can delete it to get some more space. And now we will continue with that exact expression, so I will write it here. So we know this is going to still pi over 4, but we now managed to rewrite it to tangent still 2x, that didn't change, times tangent x minus 1. But now it's going to be paradoxically a little bit easier, even though it might not seem, because this new expression will let us do trigonometric substitutions and get to some more results, not that hard. So first of all, we can view this as sine 2x over cosine x, for example. So we can see this as such. This we can sine x over cosine x as well. So let's see how we can first rewrite things. Well, actually, if we want to just rewrite everything, we can do this. We can still do sine 2x over cosine of 2x. Because this will actually go to 1, so that's quite nice to realize, times, that's still all inside the argument of the limit, sine x over cosine x, that's tangent x minus 1. Now, I will take the common numerator here, so sine x minus cosine x over cosine x. We can rewrite this thing, it's equivalent. And at this point, what we can do is also realize sine 2x, actually, x is pi over 4, so sine of pi over 2, that's the 2x, changing it to pi over 2, that is actually going to 1. So that's fine, so we kind of got rid of that. And then let's play with the rest here. So we will have limit x to pi over 4, sine x minus cosine x at this point, over cosine 2x times cosine x. But cosine 2x is also rewritable by a trig identity as cosine squared x minus sine squared x. And that is the same like cosine x minus sine x. So sine x minus, we still have to write the limit. though. So this is all equal to limit x goes to pi over 4 sine x minus cosine x, everything cosine x minus sine x. There's the a minus b times a plus b cosine x plus sine x. We're just rewriting using some trig substitutions, trig identities, and some algebraic rules, and still cosine x here. So now it's a long expression. It seems like a long expression, but we can cancel out these two things just adding. Basically, if I say minus here, and I also put a minus here, then this thing is same like this thing. So these two things can be cancelled as long as the minus is retained. So all this will now be minus 1 over cosine x plus sine x times cosine x. But now we should realize that this is square root of 2 over 2, square root of 2 over 2 under pi over 4. And so what we will get is this times 2 times square root of 2 over 2. But this is square root of 2 time, all of this is square root of 2. This is square root of 2 over 2. So this is 1. So we get minus 1 as a result. So from all this manipulation, we go to minus 1. So this original thing, the exponent, is equal to minus 1. And therefore, this whole limit, let's delete these few steps here, basically is we just have to substitute back that limit of e to all this. We now found that we were the whole time taking care of the exponent only, is e to whatever we found the exponent to be, and that is this minus 1. So e to the minus 1 is the result.